Welcome back to AI Podcast. I'm Nate, your commentator today, and with me is Maya, our thoughtful listener. Hi, Maya.
Hey Nate, happy to be here. What are we unpacking today?
A recent ICLR paper titled No Need to Talk, Asynchronous Mixture of Language Models, also nicknamed Small Talk LM. In one line, they train several independent language model experts, then use a lightweight router to look at a short prefix of the input and pick just one expert to handle the whole sequence. The result is better language modeling quality at roughly similar compute and far less communication between machines during training.
So the headline is, More quality without the chatty, high-bandwidth training that big models usually need. Got it.
Exactly.
Who's behind it?
The work is led by Anastasiia Filippova with collaborators at Apple, with Filippova also affiliated with EPFL. We'll keep it to representative authors so we don't list a whole roster.
Sounds good. Before we dive into the method, what's the core pain point they're trying to solve?
Two big ones. First, training large language models usually means constant synchronization of gradients across many machines. That's a heavy communication tax. Second, at inference time, a lot of sparse mixture systems route tokens among many experts on every step, which again depends on fast interconnects and complex coordination. The paper asks, can we avoid most of that chatter and still get strong performance?
Right, because even if compute is cheap, bandwidth and coordination are often the real bottlenecks.
Exactly. Prior lines of work tried to reduce communication during training, things like local updates or compressed gradients, but they often lose some quality. And token-level mixture of experts models do save compute per token, yet they still require frequent communication because they shuttle tokens to different experts over and over. Another category assigns data to experts by clustering or using metadata. But that can depend on seeing the whole data set in advance or having labels that won't exist at inference time.
So the gap is a method that lowers communication during training and keeps inference simple without relying on handcrafted clusters or extra metadata.
That's the gap this paper targets.
All right, how do they do it?
The key idea is a hard mixture of language models with prefix routing. Picture several independent experts, each a normal decoder-style language model. Then there's a tiny router, which is actually a very small language model per expert. Given a short prefix of the input, each tiny router estimates how well its expert would model that prefix. The system chooses the expert with the highest score, and that one expert generates the entire continuation.
So the router is like a quick taste test. It sips the opening of the text and decides which expert should take the full glass.
Exactly. Because the choice is made once per sequence, inference stays simple. No token-by-token shuffling across experts. And training is split into two stages. First, train those tiny routers and use them to segment the training corpus so each sequence gets assigned to one expert. Second, train the experts independently on their assigned data. That independence means machines running different experts barely have to talk.
I'm curious, if routing is based on a short prefix, how short is short?
The paper shows that even short prefixes can work well while still improving over a dense baseline.
Nice. And they must have some way to prevent all the easy texts from piling onto one expert.
They do. During data assignment, they balance the load so each expert gets a fair share. At inference time, though, the system just picks the best expert based on likelihood. No enforced balancing there.
Let's talk experiments. What did they train and how did they compare?
The experts are conventional transformer language models at sizes that most labs would recognize, and the routers are tiny by comparison. They trained on a large-scale web corpus, used a standard context length, and mainstream optimizer choices. For comparisons, they kept training tokens and overall compute fare, and matched inference cost by ensuring that calling a single expert is comparable to a similarly sized, dense baseline. Evaluations included perplexity and a set of standard zero-shot benchmarks.
So apples to apples on tokens and budget, and then check both perplexity and downstream accuracy.
Right? The top-line results show better perplexity than dense baselines at roughly the same training footprint and competitive or better performance on a majority of the downstream tasks. One detail I like: the router doesn't need to be big. A very small router works fine, which keeps overhead down. Another point: short prefixes suffice for effective routing, and their likelihood-based approach outperforms simple clustering strategies.
That's reassuring because tiny routers and short prefixes keep the system practical. What about the systems angle? How much talking do the machines actually avoid?
Quite a lot. Because experts train on their own data shards after routing, there's no constant gradient synchronization between them. The router training and data assignment involves some coordination, but it's occasional and lightweight compared with standard synchronous distributed training.
So the title, "No Need to Talk," isn't just a catchy line. It reflects a real reduction in communication.
Exactly.
Let me push a little. How strong are the gains? Are we talking marginal improvements that depend on careful cherry-picking, or something more robust?
The gains in perplexity are consistent across several settings, and the downstream results are generally on par or better than dense models at comparable inference cost. The author's narrative is that specialization matters. Different experts learn to model different types of text, and as you add more experts, specialization becomes clearer without collapsing onto a few.
That story makes sense. Specialized models often win when the router picks well. Any caveats?
A few. First, pre-training focused on a single large web corpus and multiple-choice style benchmarks, so we'd want to see broader evaluations like open-ended generation, instruction following, or multilingual tests. Second, the method routes once per sequence. That's simple and efficient, but for very long documents, topics can drift. Dynamic rerouting mid-sequence might help, and it isn't explored here. Third, real-world speedups depend on your hardware and network. The paper accounts for compute fairly, but wall clock time on different clusters can vary. Finally, at the time of publication, there wasn't a public code release in the paper text, so reproducing the exact data assignment pipeline may take effort.
All reasonable. In practice, people will want to know whether they can plug this into their stack soon, or if it's still research.
I'd call it research with a practical flavor. The building blocks are standard: transformer experts and tiny language models as routers, and the training procedure is straightforward once you implement data segmentation and balancing. A production rollout would still benefit from reference code and systems benchmarks.
Could you summarize the main engineering takeaways for someone deciding whether to try it?
Sure. If you're bandwidth constrained during training, this approach reduces cross-machine chatter by letting experts train independently. At inference time, you run just one expert, so the cost stays comparable to a dense model of that expert's size. Routing uses a short prefix and doesn't require metadata or heavy clustering, and the router can be very small, so overhead remains low.
And on the research side, what would you like to see next?
3 directions. First, adaptive or hierarchical routing that can redecide mid-sequence for very long or multi-topic texts. Second, broader evaluations including instruction-tuned tasks, open-ended generation quality, safety and robustness, and multilingual benchmarks. Third, a systems study that reports end-to-end throughput and latency on different interconnects, and explores fault tolerance when experts train independently and perhaps join or leave elastically.
I'd add one more. If they release the router and expert training code, plus a plug-and-play data segmentation script, teams could validate the results more quickly.
Completely agree.
Before we wrap, I want to restate the core message to check my understanding. Small talk. LM trains multiple independent experts, uses a lightweight router to select one expert from a short prefix, and sticks with that expert for the whole sequence. That reduces communication during training and keeps inference simple while improving perplexity and performing strongly on standard evaluations.
Perfect summary.
Then, my last question: if I'm a practitioner with a mid-sized budget, is there any hidden gotcha?
The main gotcha is implementation detail. You'll need a clean pipeline to train the tiny routers, segment your data evenly, and manage expert checkpoints. None of that is exotic, but it is engineering work. Also, measure wall clock performance on your own cluster. Compute budgets on paper don't always map to throughput in practice.
Fair point. This was clear and balanced. Thanks, Nate.
Thank you, Maya. That's it for today's AI podcast. If you're exploring mixtures of experts and want less network chatter without sacrificing quality, this paper is worth a read. See you next time.